So far, we've already looked at some pretty simple exponential functions, simple meaning that they just grow by the same amount when x goes up by 1. Um, but in the last example, we saw the phone tree example in class. The last problem we did was x1 is going up by 5, so it became a little bit more difficult to find the function. So again, if x is going up by 1, that's pretty easy. We can see that from 2 to 8 is times 4, times 4, times 4, times 4. We show our work. We see 2, 2 times 4, 2 times 4 times 4, 2 times 4 times 4 times 4 times 4, blah, 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 blah. And then when we try to write this in a shorter way, we see this one is 2 times 4 squared, 2 times 4 to the third, 2 times 4 to the fourth. And we see that when x is 5, the exponent is 4, and we can look up, and when x was 4, the exponent was 3, etc. And it's very easy to see that the exponent appears to be 1 less than x. So when x is 100, we know that that's going to be 2 times 4 to the 99th power, because 99 is 1 less than our x, which is 100. And when we just have x to get our formula, our equation, we see it's 2 times 4 to the x minus 1. Why? Because the exponent is 1 less than our x, and we get our function. So we know how to do that, no problem. We've seen several examples like that. But let's review the phone tree again. So with the phone tree, we had this table right here. We put in 100, we put in x to help us try to find our rule. We know that it's times 3, times 3, times 3, times 3. We've done this. We did it in class. So we have our work, and we start with 1 times 3. So 1 times 3 times 3, this is pretty easy so far. This doesn't look any harder than any other example that we've done. Here we have 1 times 3 to the first, 1 times 3 to the second, 1 times 3 to the third, 1 times 3 to the fourth. So far so good. It doesn't seem much harder. But if we look, the exponent isn't 1 less than our x anymore. In fact, we have to ask the question, what is the relationship between x, which is our independent variable, and what is changing in the work, which is the exponent? Right? So we need to find a connection between our x and our exponent here. So we need to look. So when x was 5, the exponent was 1. When x was 10, the exponent was 2. When x is 15, the exponent is 3. When x is 20, the exponent is 4. Okay, I'm not sure what's going on here. We need to, because if we want to do when x was 100 and figure out what the exponent is there, we have to find a pattern or relationship. Well, to get from 5 to 1, you could subtract 4. So is it x minus 4? Well, 10 minus 4 is 6, not 2. And when x was 10, our exponent was 2. So that doesn't work. But you can also divide by 5. 5 divided by 5 is 1. 10 divided by 5 is 2. 15 divided by 5 is 3. That seems to work. So the exponent is x divided by 5. So when x is 100, the exponent should be 20, because 100 divided by 5 is 20. So we have 1 times 3 to the 20th power. And we just have x. It's 1 times 3 to the x divided by 5. So that's our rule. So we're always looking for a relationship between our x and our exponent. Sometimes that relationship is easy to see, and sometimes it's more difficult, but that's what you need to look for. What's changing in our x and what's changing in our work. And in this case, it's the exponent. So that's what we need to find. So we have our rule, f of x is equal to 3 to the x divided by 5. Almost all of you got this in class already. That was great. Let's look at another example. So let's say we're doing an example and we get when x is 0, g of x is 6. When x is 4, g of x is 12, 8, 24, 12, 48, 16, 96. And we know later we're going to do our 100 and our x, so we can go ahead and put those in now, even though we're not thinking about them yet. And we're looking for a pattern. So we notice that 6 times 2 is 12, 12 times 2 is 24, 24 times 2 is 48, 48 times 2 is 96. So of course we do our work next. 6. 6 times 2. To get to 24, we did 6 times 2 times 2. To get to 48, we did 6 times 2 times 2 times 2, etc. And we can write this in a shorter way: 6 times 2 to the first power, 6 times 2 to the second, 6 times 2 to the third, 6 times 2 to the fourth power. And again, we have to ask the question: what is the relationship between x, our independent variable, and what is changing in the work, in this case the exponent? So when x was 4, the exponent was 1. When x was 8, the exponent was 2. When x was 12, the exponent was 3. When x was 16, the exponent was 4. So how do we get from one to the other? Well, 4 divided by 4 is 1. 8 divided by 4 is 2. 12 divided by 4 is 3. So it looks like we're looking for the exponent is x divided by 4. So for 100, 100 divided by 4 is 25. So we have 6 times 2 to the 25th power. And for x, it's 6 times 2 to the x divided by 4 power. We know this because we saw that the exponent was just x divided by 4. So there's our rule. But this brings up an interesting point, because what if we wanted to keep exploring? What if x was 2? Well, if x is 2, we should have 6 times 2 to the 1/2 power. Is that supposed to be 9? Because 9 is halfway between 6 and 12? I don't know. Let's try to explore it. So we're wondering if 6 times 2 to the 1/2 power is 9. Let's try to think about that. Let's look. Is it 6 times 2 with only writing half? Like, what is 2 to the 1/2 power? That doesn't make any sense. 2 to the 1/2 power is part of a 2? It doesn't make sense to think about it in that way. So it's really hard to think, how are we going to get this? Well, let's look at the graph. So how do we find 6 times 2 to the 1/2 power? Here's our table. I made it a little smaller to fit. And this is what's going on here. Let's look at the graph. This is the graph of f of x, or g of x, is equal to 6 times 2 to the 1/2 power. That's our graph. Okay, it looks curved. Let's zoom in. So we're zooming in. Now it looks straighter. It's really not. It's just as curved. It's just that we've zoomed in, so it seems to be straighter. But it's not. If you look closely, you can tell that it's actually curved. And we are guessing that when x is 2, g of x is 9. That's what our guess was. So let's graph that point, 2, 9. There it is. Is that on our graph? Is that on the graph of g of x equals 6 times 2 to the 1/2 power? No, it is not. It's clearly above it. So that can't be our answer. So how do we do this? Well, we could just use the formula, the equation. G of 2 is going to be 6 times 2 to the 2 over 4, which we know is 6 times 2 to the 1/2 power. We did that in the last slide. So how are we going to figure that out? Well, we have calculators, so let's just use it for now. And we'll type it in. So we have 6 times 2 to the 1/2 power, 0.5. And what do we get? Whoa, 8.485281374238857. Interesting. Didn't expect that to happen. So what we found was that g of 2 is approximately 8.49. I rounded. G of 2 is approximately 8.49. So this point here is 2, 8.485, blah, blah, that number that's in the calculator. So how did we get that? How does that make sense? How can 6 times 2 to the 1/2 power be 8.49? Well, we know 6 times 2 to the 0 power is 6, and 6 times 2 to the first power is 12. So we know that 6 times 2 to the 1/2 power has to be between 6 and 12. The graph showed it was not 9. It was below 9. We could also see it was above 8, but why is it 8.48528? Blah, 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 blah. Well, that takes a little bit more exploration. So tune in next homework for what are fractional exponents. If you really want to figure this out, little hint, you can use your calculator and type in 4 to the 1/2 power, 9 to the 1/2 power, 16 to the 1/2 power, 25 to the 1/2 power, and see if you notice anything. That's the end of the slideshow.